Steam distillation is often used to remove a volatile oil from plant material. And the reason it's used is that the saturation pressure of that oil is relatively low. So another way of looking at it is the boiling temperature is high. And to try and boil it would require going such a high temperature that you would start decomposing or reacting those volatile components, the oils. So the idea, if we had something with a saturation pressure, so the saturation pressure, the volatile, is less than 1 atmosphere pressure. So we're below its normal boiling temperature. Then we have air above, and in order for us to evaporate and collect the oil, the volatile, it requires that that volatile component diffuse through this stagnant air layer, very slow process. And so what we're looking at, if the pressure is 1 atmosphere, here's the saturation pressure of our volatile component, and then here is the pressure of the air, where we're looking at this as the pressure, then the total pressure, the sum of the two. So what steam distillation does is add water to the liquid, or the solid liquid in the plant material, because water's evaporating at a lower temperature allows us to remove this volatile component. So let's look at what diagram would show. So here is the saturation pressure of the volatile component, and then this is the saturation pressure of water. In most cases, that volatile component's an organic and oil, it's not miscible with water, so the total pressure is just the sum of these two, which then is the total pressure. And if we're at a temperature where the total pressure is 1 atmosphere, then we get boiling of both components. We can look at that on a pressure temperature diagram. So this represents the volatile component. So its normal boiling point is very high. Here's the normal boiling point of water at 1 atmosphere, 373 Kelvin. When we have immiscible liquids, then the pressure above them is just the pressure of the water, saturation, plus the saturation pressure of the volatile. And we can add them together because they're immiscible. So that means now the boiling point of the mixture is here. It's lower than the boiling point of water, and it's much lower than the boiling point of the oil. And so therefore we can remove this volatile from the liquid phase or liquid solid phase at a temperature where we don't decompose that volatile component. The other way of looking at this is corresponding. This diagram is at this temperature. Here's the saturation pressure. The volatile, here's the saturation pressure. The water, we add them together, we get the total pressure, 1 atmosphere, so we get boiling at that temperature. Now once we've boiled over the mixture of water and the volatile and condensed it, separation is easy because they're immiscible. We're going to get 2 phases, and then 2 liquid phases are very easy to separate. Now instead of adding water and doing steam distillation, it's possible to do vacuum distillation, namely pump away the air. So we're going to now have that stagnant air layer and evaporate the volatile that way, and that's certainly done, but steam distillation clearly is used. It also would work if we have something that is miscible, so then we have an additional separation step. But if it's miscible and we look at a diagram, for ideal, if this is the saturation pressure of water, and this is the saturation pressure of the volatile component, you can see if we mix them together, we can get a pressure that's much higher than the saturation pressure of the volatile component. So for example, if this is 1 atmosphere, this mixture will then evaporate, and we can condense it, collect it, and go through another separation step.